Hardness of water. So before we get into this hardness of water, just let us see the classification of water on the basis of the ability of water to form lather with the soap. Normally when you are adding soap into water, it forms lather. But the extent to which it forms lather varies from one water sample into another because of the soluble salts present in it. So water which forms lather readily with the soap is called as soft water. Soft water which lathers readily with the soap. Water which forms lather readily with the soap is called soft water. The other one, our topic of interest, hard water, which does not form lather readily with the soap. Water which does not form lather readily with the soap is called as hard water. Instead, the soap which we added is reacting with the salts present in water, forming scum. It's a precipitate-like substance. So water which lathers readily with the soap is called soft water. Water which does not form lather readily with the soap is called hard water. So the hard water, instead of forming lather readily with the soap, it will form lather, but we have to add excess of soap. You can get lather only after the removal of the soluble salts as a precipitate, as a scum. Then only the excess soap which you are adding can form lather. So this hardness is a major problem both for a civil engineer and even in washing profession. Anyhow, now let us move to hardness of water. So what are the substances causing hardness to water? And what are the types of hardness? Hardness can be classified into two types. One is temporary hardness, another one is permanent hardness. Temporary hardness is otherwise called as bicarbonate hardness. This is called as non-bicarbonate hardness. So hard water can be classified into two types. One is temporary hardness, another is permanent hardness. Temporary hardness is mainly due to carbonates, and thereby it is called as bicarbonate hardness. Permanent hardness is not caused by bicarbonates, it is caused by chloride and sulfates of calcium, magnesium and heavy metal salts. So let us see one by one. So this temporary hardness is otherwise called as bicarbonate hardness. It is due to carbonates. It is due to bicarbonates of calcium, magnesium and heavy metal salts. So temporary hardness is otherwise called as bicarbonate hardness. It is due to the bicarbonates of calcium, magnesium and heavy metal salts. Remember, these bicarbonates are soluble. So calcium, magnesium and other heavy metal bicarbonates are in soluble form. So they goes into the solution, giving hardness to water. And this temporary hardness can be easily removed by boiling. Let me take a hard water which is having bicarbonate hardness due to the presence of calcium bicarbonate. when this hard water containing calcium bicarbonate, that is temporary hardness, can be removed just by boiling water. On boiling, bicarbonate decomposes to give insoluble salt, calcium carbonate plus water with evolution of carbon dioxide. When we are boiling water, the temporary hardness causing substance like calcium bicarbonate decomposes to give insoluble precipitate of calcium carbonate with evolution of carbon dioxide, and the other major constituent magnesium bicarbonate. It is not necessary that always the bicarbonate should be converted into carbonate, so even they may be converted into insoluble hydroxides like magnesium hydroxide plus carbon dioxide. So temporary hardness is always called as bicarbonate hardness. It is caused by the bicarbonates of calcium, magnesium and heavy metal salts. Bicarbonate hardness can be easily removed by boiling water. When water is boiled, the bicarbonates are converted into either water insoluble carbonate or water insoluble hydroxide. The second one is permanent hardness. Permanent hardness is otherwise called as non-bicarbonate hardness. It is not due to bicarbonate, it is due to chloride and sulfates of calcium, magnesium and heavy metal salts. It is due to chloride and sulfates of calcium, magnesium and heavy metal salts. Chloride, sulfates of calcium and magnesium and heavy metal salts of these ions are causing permanent hardness. Permanent hardness cannot be removed like our temporary hardness by boiling. It can be removed by adding some lime or by treating it with zeolite. Expression of hardness. Hardness can be expressed as calcium carbonate. In the same way, we expressed alkalinity as calcium carbonate. So why in both the cases we are preferring calcium carbonate as a standard? The one simple thing is its molecular weight is 100, easier for calculation. And in hardness, most of the hardness causing substances are removed as calcium carbonate precipitate. Even we have seen in temporary hardness, when water is boiled, that calcium bicarbonate present converted into calcium carbonate. And even on adding lime, this calcium bicarbonate can be removed as calcium carbonate. That's why we are preferring to express hardness in terms of calcium carbonate. But while expressing that alkaline hardness as calcium carbonate, we have one problem because we don't have calcium compound alone. Some compounds like magnesium sulfate, magnesium chloride, calcium sulfate, like that we are having so many substances causing hardness. So which one, how to get the value for that? For that it is very simple. Hardness as calcium carbonate is equal to the mass of the hardness causing substance. That may be calcium carbonate, or that may be calcium sulfate, calcium bicarbonate, it may be anything. So mass of the substance, mass of the hardness causing substance divided by equivalent weight of hardness into equivalent weight of calcium carbonate. So when we divide the mass of the substance in grams divided by equivalent weight, we will be getting number of equivalents. When that number of equivalents divided by equivalent weight, then we are getting the value in terms of calcium carbonate. So next one, how this hardness is determined and estimated in laboratory. For that we are having one method. Determination of hardness. Hardness of a water is estimated by using a titration, but there is a difference between the titration which you had done earlier in alkalinity and this titration, that is our simple acid based titration, whereas this is based on a complexometric titration. So in this complexometric titration we are using a complexometric reagent EDTA, ethylene diamine tetraacetic acid. Actually the ethylene diamine tetraacetic acid is water insoluble, so its disodium salt is taken. That structure of that ethylene diamine tetraacetic acid. This is EDTA, ethylene diamine tetraacetic acid. It is water insoluble, so its disodium salt is taken. So this EDTA, ethylene diamine tetraacetic acid's disodium salt, is used as a complexometric agent here. The hardness causing metal ions calcium and magnesium will form complex readily with this reagent. Let us see the principle behind this. Estimation. So the hardness causing ions calcium or magnesium ion, when treated with EDTA, it will form a complex. That complex is calcium EDTA complex, magnesium EDTA complex we are getting. This is one case. Here we are using an indicator eriochrome black tea, that is abbreviated as EBT. Which will also form complex with these two. So both EDTA and EBT will react with or will form complex with this calcium and magnesium ions. So in a conical flask, I have taken hot water, into this when I am adding this indicator EBT, eriochrome black tea, it is forming complex readily with calcium and magnesium ion. Of course this complex is unstable. When we compare the stability of these two, this is an unstable complex So the color of the unstable complex is wine red, whereas when calcium and magnesium ion forms with complex EDTA, that complex is more stable than your indicator metal ion complex. So this complex is relatively more stable complex. So making use of the difference in stability of the complexes, we are achieving the estimation of calcium hardness of water. And this complexometric titration is carried out with a pH of 8.5 to 10. So that is very important, because only in this pH interval the complexation will take place. So let me briefly explain the principle. In a conical flask, we are taking hardness containing water. Into that we are adding indicator, and we are adding a buffer. Buffer is a substance which will maintain the pH constant. Here we are adding a buffer which is having the pH interval 8.5 to 10. That is ammonium chloride, ammonium hydroxide buffer is added into this. On adding, this EBT will combine with calcium and magnesium ions, forming a complex. That complex is wine red in color, but it is unstable. So now the solution is having wine red color. That conical flask solution is having wine red color. It contains hard water, indicator and buffer. Solution is wine red in color. Now by taking EDTA, ethylene diamine tetraacetic acid in the burette, we are carrying the titration. When EDTA enters into this complex, so this conical flask is containing the complex. So this is wine red in color. The conical flask solution is wine red in color. Now we are adding EDTA. From burette we are adding EDTA. So this EDTA, so this complex is relatively unstable. EDTA is forming a stable complex with metal ions, and indicator is freed. So this is giving you calcium EDTA complex and magnesium EDTA complex. So this is stable plus indicator is free. Once indicator is freed, we are getting green color. The end point is the appearance of green color due to the presence of free indicator present. So let me briefly explain the principle and procedure as well. So in a conical flask, we are taking hard water, fixed known amount of hard water is taken. Let me say 50 ml of hard water is taken. Into that we are adding indicator, EBT, aerochrome black tea, and we are adding a buffer to provide the pH of 8.5 to 10, because only in that basic pH this complexometric complexation will take place. On adding indicator, the color of the solution becomes wine red. That is due to the formation of unstable indicator metal ion complex. Now that conical flask solution having wine red color is titrated with EDTA, standard EDTA, we know its strength by taking in burette. When you go on titrating it, this EDTA is replacing the indicator from this complex, From this complex, EBT is freed and EDTA is forming a stable complex with calcium and magnesium. Since indicator is freed, it is having green color, so the appearance of green color is the end point for this titration. Now let us go to the actual procedure, because this complexometric titration involves so many solutions of various concentration. Let me explain how the solutions are prepared, and from that how the actual hardness is obtained. Estimation of hardness. To estimate hardness of water, we need various solutions and indicators. Let us see how it is being prepared. First one is standard hard water. That is made by it is prepared by dissolving 1 gram calcium carbonate. Calcium carbonate, all we know, it is insoluble in water. So it is dissolved in minimum volume of dilute HCl, and it is made up to 1000 ml. That solution, when you take 1 ml, which will carry 1 milligram of calcium carbonate, and EDTA, disodium salt of that EDTA, 4 gram of EDTA dissolved in 1000 ml of water, and EBT, eriogram lactate, it is dissolved in ethyl alcohol, 0.5 gram we are taking, which is dissolved in 100 ml of alcohol. And buffer, it is basic buffer, it is made by dissolving a weak base and its salt, 67.5 gram of ammonium chloride and 570 ml of ammonium hydroxide are mixed, and it is made up to 1000 ml. It will have the pH of 8.5 to 10. So pH will be in that range. So estimation of hardness involves 3 steps. First one is standardizing EDTA, and second one is getting total hardness. From that, after getting total hardness, we can get permanent hardness, and finally we can go for the summarizing. So first one, how this EDTA is standardized. To standardize EDTA, we are taking 50 ml of the standard hard water. Standard hard water is taken. With that, 10 ml of buffer is added, followed by adding 4 to 5 drops of indicator. Solution becomes wine red in color, which is titrated with the EDTA by taking in burette, and the end point is the color change from wine red to green. That is the end point. And volume of EDTA consumed is V1 ml. Here we know the volume of EDTA. By knowing the volume of EDTA, we can standardize it. That standardization is here. So the first one is standardization as EDTA, and V1 is the volume of EDTA consumed. Before that, 1 ml of standard hard water is equal to 1 milligram of calcium carbonate. Here we have taken 50 ml of standard hard water, so it is equivalent to 50 milligram of calcium carbonate. And this 50 ml standard hard water, which contains 50 milligram of calcium carbonate, consumes V1 ml of EDTA. Therefore, 1 ml of EDTA is equivalent to how many milligrams of calcium carbonate? That is, V1 ml of EDTA is equal to 50 milligram of EDTA. Therefore, 1 ml of EDTA, V1 consumes V1 ml of EDTA consumes 50 ml of hard water. Therefore, 1 ml of EDTA is equivalent to how many milligrams of calcium carbonate? So, if we know the volume of EDTA consumed, we can get the amount of calcium carbonate present in that water. So 1 ml of EDTA is equal to 50 by V1 milligram of calcium carbonate. Let me say our sample consumes some 10 ml of EDTA. We can get the milligram of calcium carbonate. So V1 50 by V1 into 10 will give so many milligrams of calcium carbonate present in that hot water. So now let us move to total hardness estimation. So now we have standardized EDTA. 1 ml of EDTA is equal to 50 by V1 milligram of calcium carbonate. So the same procedure which is used for standardization of EDTA is repeated for our sample hard water. In the place of standard hard water, we are adding sample hard water. 50 ml of sample hard water is taken here. Into that 10 ml of buffer is added. 4 to 5 drops of indicator, heliochrome black tone adding, color becomes wine red color, and titrate of the EDTA, color changes to green, from wine red to green is the end point, and volume of EDTA consumed by 50 ml of sample hard water we are getting as V2 ml. So V2 ml of EDTA is consumed by our hard water. It contains or it is equivalent to how many milligrams of calcium carbonate? We know 50 by V1 milligram of calcium carbonate is equivalent to 1 ml EDTA. Here we got consumed V2 ml. So V2 into 50 by V1 milligram of calcium carbonate hardness is present in the 50 ml of sample we have taken. So we have taken 50 ml of hard water. It consumes V2 ml of EDTA, and V2 ml of EDTA is equivalent to so many milligrams of calcium carbonate, that is 50 ml of sample hard water contains 50 into V2 by V1 milligram of calcium carbonate, but we want to express the value in terms of ppm or milligram per liter. So therefore 1000 ml contains, so V1 V2 50, so 50 contains so much, 50 ml of water contains so many milligrams of calcium carbonate. Therefore 1000 ml contains this much, V2 by V1 into 1000 ppm is the total hardness as calcium carbonate. So we have standardized and we got total hardness. Now we want to get temporary hardness. How to get it? See, temporary hardness, all we know, it can be removed by boiling the water. So take another 50 ml of sample hard water, boil it. On boiling that calcium bicarbonate. So that's all about total hardness. Now, how that permanent hardness is determined? So total hardness is the sum of temporary and permanent hardness. How to get permanent hardness alone? For that, the temporary hardness has to be removed. So temporary hardness can be removed by boiling the water. We know the temporary hardness causing substance, calcium bicarbonate and magnesium bicarbonate, on boiling, it is converted into calcium carbonate, carbon dioxide, water. If it is magnesium bicarbonate, it is converted into insoluble magnesium hydroxide plus carbon dioxide. So we are taking 50 ml of sample hard water, which on boiling, the temporary hardness causing substances, calcium bicarbonate and magnesium bicarbonate, are converted into water insoluble calcium carbonate and magnesium hydroxide. That means they are in the form of precipitate. So filter these precipitates. That means temporary hardness is removed as precipitate. Now water left over carries only the permanent hardness causing substances. So 50 ml of water is taken. It is boiled for 15 minutes to get converted all these temporary hardness causing substances into the respective precipitates. They are filtered, and that filtrate, which is free from temporary hardness causing substance, is titrated with EDTA by using areogram black tea indicator. By titrating it with, in the same manner as earlier, we are getting the volume of EDTA consumed as some V3. So V3 is the volume of EDTA consumed by the permanent hardness causing substance alone, because temporary has been already removed. So from this V3 we can get permanent hardness alone, that is permanent hardness, volume of water 50 ml, which consumes volume of EDTA as V3 ml. V3 ml is the volume of EDTA consumed. As we know earlier, the 1 ml EDTA equivalent, 1 ml EDTA is equal to 50 by V1, whereas here how much is consumed? V3. So V3 into 50 by V1 will give so many milligrams of calcium carbonate as permanent hardness, and so much is present only in 50 ml, therefore for 1000, that is V3 into 50 by V1 into we are getting V3 by V1 into 1000 ppm as the permanent hardness. So we got total hardness there and permanent hardness here. By subtracting the permanent hardness from the total hardness, even we can get our temporary hardness.